In section 2.5, we're going to take the multi-step equation concept on to a new level and work on solving equations that have variables on both sides. So what we're going to want to do in doing this is we're going to want to get the variables onto the same side by using properties of equality, again, adding, subtracting, multiplying, and dividing, and then combine like terms and solve. So it's all things we've done already in the other sections. New vocabulary is the concept of an identity. An identity equation is an equation that is true for all values of the input variable, and we'll have an example of that in just a little bit. So if I want to start off by looking at solving an equation with variables on both sides, you see I've got 8c on this side and 4c on that side. And what I'm going to want to do in order to solve that is I'm going to want to get them onto the same side. So I'm going to do that by subtracting 4c from either side of the equation. Now, I could have subtracted 8c from either side, but it's always in your best interest to try to keep the coefficient with the variable to be positive. It just cuts down on the potential for error as you continue to work on. So the next thing I would do would be to subtract 5 from either side of the equation. And then I'll get that 4c is equal to negative 16. If I divide by 4, c is equal to negative 4. Okay, so what we basically did is we got the like terms on the same sides of either side of the equation, combined like terms, and then solved. Okay, let's do that again. Here I've got the added issue of distributing this 3. So I could either distribute the 3 or divide by 3. And you'll notice 8 and 4, those are not simple numbers to divide by 3, so I'm going to go ahead and distribute. 3d plus 36 is equal to 8 minus 4d. Now I'm going to add 4d to either side. So over here I'll get 3d plus 4d is 7d. And I'm going to subtract 36. 8 minus 36 is negative 28. And then I'll want to divide by 7. d is equal to negative 4. Okay, looking at that in the context of a word problem again. I have a car dealership that sold 78 new cars and 67 used cars this year. The number of new cars sold by the dealership has been increasing by 6 cars each year. And the number of used cars sold by the dealership has been decreasing by 4 cars each year. If these trends continue, in how many years will the number of new cars sold be twice the number of used cars sold? Okay, so I know what we're comparing now is twice the number, right? So I want to compare number of used cars, number of new cars, and we're going to be comparing by in how many years. So my variable is going to be years. So let's say X is years since now. Years. Right? And if I look at the number of new cars that we sell, I have 78 new cars that I sell per year, and it increases by 6 cars each year. So my total number of new cars will be what we started with, 78, plus 6 times the number of years. And then if we look at the number of used cars, it's going to be 67, but it's decreasing by 4 cars each year, so that's going to be minus 4 times the number of years. Okay, and I know that I want the number of new cars that I sell to be double the number of used cars. Okay, so this will allow me to find how many years it takes for the number of new cars to be twice as many as the number of used cars. But you can see if it's twice as many, if I multiply the used cars by 2, then they'll be equal. Okay, so if we go ahead and again, I'd want to look at this. In this case, I would go, well, rather than distributing the 2, I could divide both sides by 2. So if I divide this by 2 and I divide that by 2, I know that I have to take 78 divided by 2 and 6x divided by 2, and then these are going to cancel, and that's going to equal 67 minus 4x. Okay, 78 divided by 2 is 39, 3x divided by 2, sorry, 6x divided by 2 is 3x. Shame on me, I jumped to the answer. Oh, minus 4x. Now if I add 4x to either side, I'll get 7x here. And if I subtract 39, so 67 minus 39, 17 minus 9 is 8, and then 5 minus 3 is 2, so 7x is equal to 28. So x will be equal to 4 years. Okay, the key was in setting up the equation, and in this case, the reason I chose to divide by 2 was because 78 and 6 were both even numbers and would be easily divided by 2. And I didn't feel like multiplying 67 by 2. I thought that would be harder than dividing 78 by 2. You should do whatever you think is going to be easiest. So some equations don't have just one answer. And we talked about this earlier. An equation that's true for all values of the variable is called an identity. So the solution of an identity is all real numbers. And then also some equations don't have any solutions. So if we take a look at this, we can look at different ways that we start working with the problem and identify that maybe it doesn't have only one solution, or maybe it has no solutions whatsoever. So if I go ahead and start with this problem and distribute, 2 times 3g is 6g, and 2 times 2 is 4. And over here I'm doing 1/2, so 1/2 times 12g is 6g, and 1/2 times 8 is 4. And if I subtract 6g from either side, I'll get 0. And if I subtract 4 from either side, I'll get 0, and I get 0 is equal to 0. Okay, this shows me that this is an identity equation. Because my variable has dropped out, this is the sign that's an identity. My variable is gone and I'm left with a true statement. 0 is equal to 0. That is true. It doesn't matter what value I put in here for g, it will always end up being true. Okay, that's an identity equation. Now let's take a look at this other problem. If I have 8z and I distribute, now this is a case where I might want to, rather than just distributing, I might want to go ahead and divide by the 4. Right? 8z divided by 4 is 2z, and that way, right, instead of distributing, I've divided both sides by 4, and that would be equal to 2z plus 1. If I subtract 2z from either side, I'll get 0 is equal to 1. And that is not true now, and it is never true. So this one would have no solution. Okay, these are both similar circumstances. When I solve the equation, the variable drops out. When I'm left with a true statement, it's an identity equation. And when I'm left with a false statement, there's no solution. Okay, so just to summarize where we're at so far with the chapter, solving linear equations in general. We want to use the distributive property to remove any grouping symbols, and remember an option is always that rather than distributing multiplication, I divide to get rid of that coefficient. I want to simplify the expression on either side of the equation. I want to use properties of equality to collect the variable terms on one side of the equation and the constant terms on the other side of the equation. And then I want to use properties of equality to solve for the variable. And then I should check my solution in the original equation. And that's it for section 2.5.